Okay, let's dive into this. Today's explainer is all about single-axis tracking, specifically horizontal versus vertical. We're going to get right into how geography directly dictates the mechanics of solar panels. We'll be breaking down section 2.37.1 of our source text today. Now, the original text we're pulling from here happens to be in Gujarati, but, the underlying engineering logic it outlines is a completely universal language. So we're going to act as your guide to extract the core, fundamental principles of how these systems are deployed, and we'll do it without getting bogged down in all that heavy outside jargon.
So, you gotta ask yourself, how do solar installations actually adapt to totally different sunlight hours? Think about it. An installation sitting right on the equator obviously has a very different relationship with the sun compared to one, say, up near the poles. Well, it turns out the exact amount of sun a specific location gets fundamentally drives the tracking technology that engineers ultimately choose to install.
Our text gives a really straightforward definition of single-axis tracking. It's simply a system of solar panels that follows the sun on one primary axis. And what's super interesting is that it splits this into a strict absolute binary. You're either going horizontal or you're going vertical, right? There are no messy hybrid setups mentioned in this section at all, just a very clear choice based entirely on the environment.
First up is horizontal axis tracking. Try to picture a central, flat line running perfectly parallel to the ground, and the solar panels just pivot around that line. But when exactly does our text say this specific configuration is the right tool for the job?
Well, the source gives us a crystal clear rule of thumb here. Horizontal tracking is for short days. When a location gets very few sunlight hours overall, pivoting those panels horizontally is simply the most efficient way to capture that brief, fleeting window of solar energy. It's a quick burst. So, the absolutely crucial takeaway here is that limited light physically demands this horizontal setup.
Let's move to and see how this builds into our other option, which is vertical axis tracking. Now, if horizontal tracking is the ultimate fix for short, quick days, what do you think happens when we take that exact same axis and just stand it straight upright?
The text completely flips the script on us here. Vertical tracking becomes the absolute go-to for areas with an abundance of sunlight. We're talking places with very long days. If your goal is to efficiently track the sun across a massive, extended horizon from dawn all the way to dusk, standing that axis vertical isn't just an option, it literally becomes the mechanical standard.
And this brilliantly illustrates how the whole thing boils down to a pure, environmentally driven engineering decision. It's a beautiful contrast. Less sunlight and shorter days? Boom, that demands a horizontal pivot. Conversely, more sunlight and much longer days? You're going to require a vertical axis for sure. At the end of the day, it really is just the literal length of the day that dictates the entire physical design. So, I want you to take a second and just look out your window. Seriously, think about the daylight hours right where you live. Based on what we've just learned together, which axis tracking would an engineer likely install in your own hometown? Pretty cool to think about, right? Thanks for joining this explainer, and hey, keep an eye out for all that structured engineering logic hiding in plain sight all around you.